So this is tutorial 9, part 2. And in this video, I'm going to go over problem question 2, given in problem 2. This is about application of so-called the Stokes theorem to the calculation of line or work integrals. And in this particular problem, question 2, I'm reminding you, you are asked to calculate the same work integral or circulation in two ways. I need to start recording. Oh, yeah, it's been recorded already. Good. I was confused. So let's do question 2D. Question 2D. I chose question 2D from tutorial 9. The whole video will be devoted to this problem only. So what do we have? What is the assignment of this problem? So you are asked to calculate circulation. You can see the circle indicates that you are dealing not with the work integral, but with the circulation of the vector field F dr over some contour or some path L. So what exactly you are given? You are given 2D vector field F. Let's copy it here. X squared y plus y squared is the first component, and the second is x cubed plus 4xy. So this is a typical 2D vector field with two components only. You remember pretty well that we used to denote them P and Q, shorthand notation. Okay, what about the path or the contour along which you need to travel? Let's write it down here. Let's plot it here. So you are given this path as a description. So this to tell you start moving from point 0, 0. This is actually origin. Let's denote it by letter O. So it has coordinates 0, 0, of course. You can write them here. Then go to the point with coordinates 1, 0. 1, 0 is located here, and we can denote it as A. Finally, then go to the point with coordinates 1, 1. It should be somewhere here. So let's denote it with letter B. Coordinates 1, 1. And finally, go back to point O. So what does it mean? It means that our path is closed. We get a closed contour. And it could be written like now, with arrows showing the direction of your movement. So it looks like this. So this is our contour. This is our contour given in black. It consists of 3 segments, as you can see. And this is what a little bit annoying, because every section has its own equation. And that is why you don't know which equation exactly you need to use. But you know, the work or line integral has many wonderful properties. And one of them says that if your path or contour consists of several segments, then it means that your line or work integral gets split into the sum of terms. Each term is taken along each segment of this path. But you know, I'm getting ahead of the assignment because I didn't tell you what the assignment is. The assignment is to calculate this integral. Let's denote it by capital I. It will be much easier than to rewrite it all the time. And you are asked to calculate. So calculate integral I by two methods. The first method is like as a line integral, they say, as a line integral. What does it mean? Just calculate directly using the equations of these segments of this path. And the second approach, the second method they ask you to apply, using so-called Stokes theorem. Stokes theorem. So you need to apply both methods, and the answers should be the same, pretty obvious. So let's dive into this problem. So the first assignment is to calculate them as a line integral. In this case, as already mentioned before, you should take into account the equations of this curve, of this path or contour. We noticed that our path, even though it's closed path, but it consists of 3 different sections. In this case, the whole integral, the whole work or line integral, gets split into the according number of terms. Let's write it down as a property. It's a very well-known, famous property of the work integral. So let's write it down. If your path, so contour C, can be represented as the union of two sections. I'm writing this general rule only for two sections. Of course, it could be generalized to any number of sections. Then what? Then what? Then our work integral along this path, let's denote it IC, should be split into the sum of two integral, the first integral of the same equation, of the same expression along the first section, plus integral along the second section. It can be written something like this: integral of the C1 plus integral of C2. It wasn't a very good idea on my part to put a circle around this integral, because this property holds true not only for circle integrals, circulations, but also for just work integrals. So even if you erase this circle, it will still hold true. Okay, so in our case, we have even three sections. That is why our integral, which is let's write down the equation of our contour. It's OABO. So this is the whole contour. And now we should split it into the sum of three contours. The first integral I will be along contour OA only, plus the second segment will be along this vertical line OB, and finally the last section will be, oh no, it's not OB, sorry, AB, of course, I made a mistake. And the last section should be noted like BO. Note, it's not OB, it's BO. It should reflect the direction of your movement. It's super important, of course. So this is our main approach when we want to calculate the work integral or circulation, which is practically almost the same, using just, like a line integral. So what can we do? We can write our integral here again, our I, and then we need to do it in three steps. We are going to calculate this one, then this one, then this one, and finally after that we need to sum up them. Okay, let's write our integral. So it was written in this form, in this general beautiful form only, but we need to rewrite it more clearly for us. As you remember, this could be written as pdx plus q dy. I'm rewriting this letter C again, denoting the whole path. And let's substitute our concrete expressions for P and Q. So our P is here. It's x squared y plus y squared dx. This is P dx. Plus Q. I'm running out of space. So Q is x cubed plus 4xy dy. And this is the notation of our whole curve. So this is the beginning. This is our template. And now we are going to go over each segment one by one, because each segment has its own different unique equation. So I'm going to keep the whole integral here on the screen. This notation is most important. Okay, let's start. So the first section is OA. This is a super simple section, but nevertheless, what is the equation of this curve? It's not even curve, it's a straight line. Of course, it's a super easy, super simple straight line which coincides with x-axis, and that is why it has equation y is equal to 0. Let's write it down. Y is equal to 0. It means that wherever we see y here in this expression, you remember, of course, quite well that the main problem with this work integral, it looks very weird because it has two variables, x and y, and we want to get rid of one of them. So in this particular segment, our y is equal to 0, and that is why wherever we see y, we always substitute it with 0. It means that finally, eventually, we'll be left with one letter, one variable, only x. And that is why we should know how x changes when we move along this line. It's super easy. You can see that you start in point O, which corresponds to x is equal to 0, and you finish your journey in point A, which corresponds to x is equal to 1. It means that x changes from 0 to 1. Okay, so we are prepared, everything, and now we are ready. So I'm putting this integral in front of our eyes on the screen. And what I'm going to do, I'm going to write this expression again. Let's call it I along path OA. This is the first term in our whole idea. So I'm going to substitute y with 0 here, wherever I see it. Okay, let's rewrite. This is integral x squared times what? Times 0 plus 0 squared dx. I'm just copying everything like a robot. So x squared then plus for x times 0 and d0. So that's, as you can see, at least letter y disappeared because it was substituted by 0. But what does it mean? You know, if you look closer now, the whole first term turns into 0 because 0 plus 0 is 0. 0 times dx will be 0 anyway. Okay. What about the next term? But things are even more beautiful than the next term. You can see d0 here. What is d0? d0, according to the rule, how should we calculate differentials? Do you remember we discussed it last time? You should differentiate this function which is under differential 0 prime dx, but 0 prime is 0 again. So the next term is 0 as well. So the whole integral of 0 is always 0. It doesn't mean what kind of integral we have, whether it's double integral or ordinary integral. Integral of 0 is always 0. It's always one of the properties of all sorts of integrals. Okay, so the first term and the sum turned out to be 0. Quite nice, very nice news. No problems at all so far. Okay, let's move to the second section, which is AB. I'm tempted to write OB all the time, I don't know. Let's have a look at our graph. And you can see this is a vertical line. And of course, you immediately realized what is this equation. The equation is x equal to 1. This is a typical equation for vertical line. So let's write it down. X is equal to 1. It means that when we take this integral again, wherever we see x, we need to plug in 1 instead of x. We'll be left with one letter y, this time only. And we need to realize how y changes when we travel along this line from point A to point B. Of course, it can easily be seen that y changes from 0 to 1. Okay, let's write it down. Y, it changes from 0 to 1. So now we are ready to apply this to our integral, which is in the yellow frame. So this time it will be I with subscript O, AB. Oh my gosh, AB. Okay, AB. So what do we have here? Wherever see, so the equation of our line is x equal to 0. So it will be 1 squared times y plus y squared b of 1, by the way, here. Okay, let's move further on. We'll discuss it later. So x is equal to 1. 1 cubed plus 4 times 1 times y dy. And so we are left with letter y only. That is why we need to recall that our y changes from 0 to 1. So we are almost ready. All we need to do now, we need to simplify this expression. But you know what? We are lucky again. Look at this. D of 1. What is D of 1? According to the rule as to how to calculate differentials of the function, we need to differentiate this 1 times dx. But you know what? The derivative of the constant is always 0. So again, the whole first term turns into 0, which is quite, nice. What about the second term? The second term is quite normal. This is 1. The next term is just 4y and dy. So we were very lucky that our first term disappeared completely, and we have to deal with this relatively simple integral. So let's start calculating it. What is the antiderivative of the first term? Y. Of course, y with vertical bar from 0 to 1. What about the second term? The antiderivative y is y squared divided by 2, so 4 and 2 get cancelled out, and we finally have 2y squared. 2y squared from 0 to 1. Now we need to substitute. So if you substitute 1 minus 0, we'll get 1 minus 0 here. So this will apply to the first term. What about this one? The best approach is to pull out 2 out of this expression and to do this substitution only with y squared. So it will be 1 squared minus 0 squared. As you can see, I write everything in great detail because I want to avoid careless mistakes. 1, so the whole term will be 1, and this will be 2 times 1 will be 2, so 3. So it means that our second term in this sum will be 3. So remember, this was 0, this plus 3, and let's see what happens with the last term. So last term, let's write it here, number 3. Section number 3 is BO. Note that it's not OB, as you might be tempted to write BO, because your notation should reflect the the direction in which you move. Maybe you can recognize this straight line immediately. This is a very famous straight line, which is y is equal to x. That is why we can write down the equation of this segment y is equal to x. So wherever we'll see y, we substitute it by x, which means that we'll be left with x, with one letter x, with one variable x already. It means that after that we will need to figure out how axis changes when we move from point B to point 0. As you can see, at the start point, which is B, x is equal to 1. At the finishing point, x is equal to 0. That is why we need to say that x changes from 1 to 0, not from 0 to 1, as you might be tempted to say, from 1 to 0, because this is our given direction in which we need to move. So remember about it. It looks weird at times, but that's how this line of work integrals works. Okay, so now we need to write. So I, the last term, I integral along line section BO needs to be derived from this expression in yellow frame when we substitute y with x. Oh, it's super easy. So x squared times x instead of y plus x squared dx. This was the first term, and the second term will be x cubed. It's just copied, and now we have 4xx plus 4xx times x, I mean. And instead of y, we write x as usual. So letter y disappeared, and as we noted, just noted a second ago, x changes from 0 to 1, not vice versa. Okay, so it looks like we need to simplify this expression. At the same time, we can see two terms here, two big terms. This is the first big term, and this is the second big term, and they have something in common. Namely, they have this differential, like a common factor. So we can pull out this common factor, putting it to the right, of course. So it will be 1 from 0. Now this term will be x cubed. This is plus x squared. And this term will be x cubed again. And here we have 4x squared. And as I promised, I'm pulling out differential dx and put it to the right. We need one more step. We need to simplify this expression definitely, because you can explicitly see like terms here, of course. So let's do it. Integral from 1 to 0. So these two guys are like terms. They will give us 2x cubed, of course. As well as these two guys, they are like terms as well. Plus 5x squared dx. And now we only need to calculate this. Okay, I'm going to save space a little bit. So what is the antiderivative or integral from the first term? It will be 2x to the power 4 divided by 4. But you know what? 2 and 4 gets cancelled. And that is why I'm tempted to write this simplified expression immediately. And the second term will give us 5x cubed divided by 3 from 0 to 1. From 1 to 0. 1 to 0, by the way. So now we need to calculate it very, very carefully. We can't afford to make mistakes, because it will reduce our score in your test or in your exam. So it's very important. So what do you need to do? We need to write very, very carefully. So looking at the first term, I realized that 1 over 2 should be treated as a common factor, and it's much more convenient to substitute 0 and to plug 0 and 1 instead of x in this expression only. And it leads us to 0 to 4 minus 1 to the 4. This is the best approach, as I mentioned many times before. What about the second term? Here we explicitly see common factor 5 over 3, which should be pulled out. And now you look at x cubed only. So it will be 0 cubed minus 1 cubed. If you write in so much detail, you will never make these careless, annoying mistakes. So, okay, what do we have here? We have 1 over 2 times minus 1, of course. It doesn't need any discussion, of course. 5 over 3 times minus 1. So it will be essentially minus 1 over 2 minus 5 over 3. We need to write 3 here, 2 here, and will be minus 3. Minus 10 will be, I made a mistake, I think. Or maybe not. So it's 2 here. Yeah. Minus 13 divided by 6. So we are almost there. We're almost there. And now we need to calculate the whole integral. So let me remind you that the whole integral along the whole path, which is OABO, we split it into the sum of 3 terms. The first term IOA plus integral along the second section, and plus integral along the last section, which was BO. And now we only need to substitute our results. The first integral was 0, the second was 3, and the last one, the current one, is minus 13 over 6. And now we need to calculate it. So we can write 6 here. 18 minus 13 will be 5. 5 over 6. So this is our result. So that's how you can calculate. This is the general rule as to how to calculate work integrals. You just need to treat them as, as line integrals. But remember, in this particular question, problem 2, you from tutorial 8, from tutorial 9, sorry, you are asked to do it using two methods. You are also asked to calculate the same integral, using the Stokes theorem. So let me remind you, assignment number 2 was do the same thing, calculate the same integral use Stokes theorem. Stokes theorem. So it turns out we need to discuss this Stokes theorem first. Stokes theorem. Okay, what is this Stokes theorem is about? It's about integrals along closed contours only. So let's make a plot first. So you are given contour, which is a closed path. So this is our contour C. And you should travel along this contour in the opposite direction. Opposite direction means counterclockwise in mathematics. You noticed it. Counterclockwise. Clockwise. It's considered to be positive direction in mathematics. We can even write something like this: C plus. It means that contour traveled in this positive direction. Okay, and you are asked to calculate integral along this circle path, and I rewrite sign plus here, indicating that I'm moving in the opposite not in the opposite, in the positive direction. Sorry, and the integral itself looks like this. So this is actually a particular case of the Stokes theorem for 2D case. I want to point it out to you. It's only for 2D case, because in general in 3D case, Stokes theorem looks much more serious, much harder. This is the particular case only for 2D field. Okay, so how it can be calculated? We already learned the first way is just to like a previous method. You need to write down the equation of this curve. You need to substitute into integral and so on, which can be really annoying, because sometimes, it's just like in the previous case, your path could consist of several segments, and it's quite a long story to deal with each segment separately. What is the next method? If you look at this curve, this plot, you realize that this enclosed circle always contains some region D inside it. And region D is always associated in our mind with double integrals. And it turns out that Stokes theorem is exactly about double integrals. It turns out that this integral could be calculated by transferring to double integral over this region D. But you need to write down the expression, the function. So the function is dq over dx minus dp over dy and dx dy. So this is a formula. This is a famous Stokes theorem for 2D case. 2D case. And this, remember, this sign plus is very essential. It means that this formula only works when you move along the contour in a positive direction, which means counterclockwise. But you might ask, what shall I do if they ask me to go in the opposite direction? You should recall the famous property of this line of work integral. If you change the direction of your movement along some line, it means that you need to put a minus sign in front of your integral. That's it. So this formula will be changed a little bit, and that you need to put minus here, or maybe here. I don't know. That's better. Okay. So let's do our problem once again, but using Stokes theorem this time. So this will be assignment 2. We are doing assignment 2 using Stokes theorem. But you know what? To do this, I think it's better to copy this curve here first. This contour. Let's do it first. So our curve consisted of 3 sections: O, A, B vertical line, and finally we have this equation y is equal to x. And this was 1, 1, if you remember. Point A has coordinates 1, 0, and origin is usual 0, 0. I'm not even going to write it. So this is our contour, and we were traveling along this contour anti-clockwise. So it means that we don't need to worry about this sign. And as you can see, of course, this contour encloses area D, which is looks like it's very convenient for dealing with double integral. Okay, so let me write this integral first. So our integral looked like, I'm just copying it here, x squared y plus y squared dx plus next term was x cubed plus 4xy dy. So this is our p and this is our q. And according to the Stokes theorem, where is it? Stokes theorem, let's have a look at it again. We need to prepare this expression dq over dx minus dp over dy and use it as a function for double integral. Okay, let's prepare a function first. So it should be dq over dx minus dp over dy. What is dq over dx? I don't think it's can be of some problem for you. So we need to differentiate this expression with respect to x. The first term will give us 3x squared, and the second term will be plus 4y. So this was the derivative of q minus, I prefer to use parentheses. Now we need to calculate partial derivative of this function p, but with respect to y. It means that x should be treated as constant. So the first term will give us just x squared plus 2y. So this is the derivative of the second term. I think we need to simplify it a little bit. 3x squared minus x squared will give us 2x squared, and these two y's will give us plus 2y. So this is our function, and we need to apply double integral to this function. Let me write this integral as y capital, because I'm sort of lazy to write it all the time. So it should be double integral over this region D, which already indicated here, from this function 2x squared plus 2y dx dy. So we prepared. And how do we usually calculate double integrals? You remember this too well. I think we need to make the transition to repeated, so-called repeated integral. And to this end, you need to have to look at your region and decide which approach is the best one. As you remember from previous tutorials, we have even 3 approaches as to how to make this transition into to repeated integral. Sorry, we can either squeeze this this region between 2 vertical lines, or the other variant is to squeeze it between horizontal lines. And finally, there is even a last option to turn everything into polar coordinate system. But I think that as for polar coordinate system, it's not a good idea. It's polar coordinate system is excellent only for circles or segments of circles, and we don't have any circles here. We will only make our integral even more complicated. I think the best approach is to squeeze it between 2 vertical lines. The simpler, the better. So, and what should we observe next? After we squeezed our region between 2 vertical lines, we need to make sure that our region D is bounded by 2 curves. The upper boundary, so-called upper boundary, which I usually denote in green, and the lower boundary. There should be only one curve, one equation for lower boundary, and only one curve equation for the upper boundary. As you can see, our region does meet these requirements. So it's just like now it's supposed to be a piece of cake for you. So if our region is squeezed between 2 vertical lines, we know the rule. We need to start writing with dx, and dx goes from 0 to 1. It shows between which 2 vertical lines your region is squeezed, between x is equal to 0 and x is equal to 1. Okay, what about the next integral? The next integral shows you the lower limit of integration, shows you the lower boundary, which has a very simple equation, y is equal to 0, but we write only 0 here. And as for upper boundary, upper limit of integration, shows you the upper boundary, which is in green, y is equal to x, and we write only x here. And now we need to rewrite, to copy our function, 2x squared plus 2y dy. And of course, and then we are almost done. But you know what? It would be very curious to find out if our answer obtained by this method should coincide with the previous answer, which was, if I remember, 5 over 6. So let's calculate the whole integral, even though it means that we have to spend some time on it. But it's super simple integral. So what is the antiderivative of the first term? It's 2x squared times y, of course. 2x squared times y with a vertical line from 0 to x. What about the next term? Next term will give us just y squared with the same vertical line. Now we need to substitute y with x minus 0, which is super easy. And at the same time, I'm going to move dx back to the right. So it will give us, so the first term will give me 2x cubed after all these simplifications, and plus x squared dx. So as you can see, this is ordinary double integral. So what is the first term? The first term is 2x to the 4 divided by 4, but 2 and 4 gets cancelled out, and that is why I prefer to write immediately x to the 4 divided by 2 immediately. I'm sort of lazy to write too much, of course. Plus x cubed. X cubed, what it is? Yeah, it's cubed divided by 3 from 0 to 1. And now what do we have here? We have 1 over 2. Let's practice this very detailed approach as I recommended to you. So I prefer to pull out 1 over 2 and substitute this 1 and 0 and write everything in much detail. 1 to the 4 minus 0 to the 4. This is the best approach during exams. So as for this term, it's better to pull out 1 over 3, and then you can look only at x cubed. So it will be 1 cubed minus 0 cubed. So this is a very good approach, as I said. So the whole expression will give you 1 over 2 plus 1 over 3. Now we need to add them together. We write 3 here, 2 here. 3 plus 2 will be, yes, we got the same answer. And looking back at these two methods, you of course realize that the second method was much easier because we did everything sort of in one go. Whereas in the first method, we have to calculate the same integral 3 times because we had 3 sections. That is why it looks like this theorem is quite handy. You know, it's quite a good theorem. And you know what? To wind up this tutorial, this problem, particular topic, I want to draw your attention at the previous material which we discussed long ago. Do you remember that the first recommendation? So you were given the task of calculating the work integral. Oh, let's discuss even circulation. It was like one particular case, but nevertheless, what was the general recommendation when you're given this task? The general recommendation is to check if your field vector field f PQ. Is it irrotational or not? So it was recommended like a first step. Check if vector field F is irrotational. Because if you discover that this your vector field was irrotational, you might be able to solve this task in a much easier way, especially in the case of circulation. Because if you discover that this field is rotational, your circulation will be 0 all the time. You won't have to do anything at all, and that is why it was strongly recommended to do this checking. But let's recall how this checking should be done. In the case of 2D, for the case of 2D field, just like here, only PQ, I gave you 2 approaches. There were 2 approaches as how to do this checking for a rotational field. Approaches. The first approach is just to calculate curl. Curl was denoted as nabla cross F. Curl is actually determinant, 3 by 3 determinant. I'm going to write down the whole thing. So here I put this nabla vector, and the last row of this determinant was PQR, but we don't have R here, and that is why you had to know the trick that how can you treat your 2D vector field? You can treat it as being 3-dimensional, but the third dimension was set up to 0. So this was sort of like a trick, how to calculate your curl. And if you found out all of a sudden that your curl was 0, you said that it means that your field is irrotational, and it means that this circulation is equal to 0 all the time. You don't need to do anything at all. But you know what? There was a second approach, like a shortcut. The shortcut, let's call it shortcut. Instead of calculating this whole 3 by 3 determinant, you can just check this equality dq over dx that is equal to dp over dy. And this equality is true if it holds. It means your field is irrotational, and you can go further on with your reasoning. So, and let's have a closer look at this equation. I think it reminds you something. It reminds you of this expression, which is under this Stokes theorem. In Stokes theorem, you have this expression under double integral dq over dx minus dp over dy. And now you can immediately figure out that if your field is rotational, which means that this equality is true, it will immediately mean that the whole expression will be 0, and that's why this circulation is equal to 0, because according to the Stokes theorem, it will be just double integral of 0 function. So it was just interesting to have a look at the whole picture once again, and from the point of view of the Stokes theorem. Maybe it's not absolute necessity, it was just curious to know. Okay, so that's it. We finished with question 2 from tutorial 9.